Hello everybody, once again, welcome back. We're going to continue our look at the 2015 Hypatia contest. We're actually going to finish up the contest in this video. We're on to question number 4. So how about we take a look at that? Hopefully you've already had a chance to look at it, and you're just here to check your answers. Alright, so question number 4. Let GCD of AB represent the greatest common divisor of the two positive integers a and b. For example, GCD of 18 and 45 is 9, since 9 is the largest positive divisor that divides both 18 and 45. Alright, the function Pn is defined to equal the sum of the n greatest common divisors, so the GCD of 1 and n, the GCD of 2 and n, the GCD all the way up to the GCD of n and n. So for example, P of 6 is GCD of 1 and n, 1 and 6, 2 and 6, 3 and 6, 4 and 6, 5 and 6, and 6 and 6. And so those values are 1, 2, 3, 2, 1, and 6. And that adds up to 15. Alright, and note, so for this question, we can use the fact that P of AB is PA times P of B for all positive integers AB that are relatively prime. Okay, that's probably a very useful fact. Alright, so light bulb. A, what is P of 125? Alright, so first instinct would be, just use this definition. We have to sum up the GCDs of 125 all the way up to 125. But that's figuring out 125 different greatest common divisors, and that's a lot of work. So there's probably an easier way to do this. And it's likely due to the fact that 125 is 5 cubed. So 125 is 5 cubed. And that means the only divisors of 125 are powers of 5. Okay. So that narrows it down. Our GCDs are going to fall into 4 categories. Either the GCD of a number in 125 is 1, 5, 25, or 125. These are the only possible GCDs, because one of these numbers is just a power of 5. Okay. So it might be a good idea to count up how many 1s, how many 5s, how many 25s, and how many 125s occur. Okay. So, how many numbers, so to get GCD of A and 125 equal to 125, it's clear that A is equal to 125. Remember, A is from 1 to 125. Okay? So that means that our sum will have exactly 125. Now, if we want a GCD of 25, a greatest common divisor of 25, then A is going to look something like 25k, where 5 is not divisible by k. So k could be 1, it could be 2, it could be 3, it could be 4, or it could be 5. Right? This corresponds to 25, 50, 75, 100, and 25, but this last one doesn't count. So we're going to have exactly 4 copies of 25 in our sum. So already we have 125 plus 4 copies of 25. Well, already we know that P of 125 is at least 225. 100 plus 125. Now, if I want a GCD of exactly 5, what am I going to have? Well, then A is going to have to be a multiple of 5. And this K here, it can't be divisible by 5. Otherwise, we'd have a factor of at least 25. And then our GCD would be at least 25. So A is between 1 and 125. That means K can be 1, 2, 3, all the way up to 125 divided by 5. So 25. So K can't be 5, 10, 15, 20, or 25. So there are 25 minus these 5. So we're going to have 20 values of A give us 5. So that means 20 copies of 5. All right, now how many give us a GCD of A? Or sorry, of 1? Well, we just need A not to be a multiple of 5. So A can't be a multiple of 5. How many multiples of 5 are there from 1 to 125? There's going to be 25 of them. And that gives us, 100 copies of a GCD of 1. So that means P of 125, well, it's going to be 1 times 1 to 25, plus 4 times 25, plus 20 copies of 5, plus 100 copies of 1. That's 125 plus 100 plus 100 plus 100 is equal to 425. And that's our value of P125. Okay, a little long for a light bulb question, but then again, this is the final question on the Hypatia. So it's not unreasonable, and hopefully some of the work we have here will help us in B, C, or D, and those are the written parts of this question. So we have P of 125. Fantastic. All right, B, written style question. If R and S are different prime numbers, prove that P of R squared S is R times 3R minus 2 times 2S minus 1. All right. Well, they're different prime numbers, so we can use this rule up here. So GCD of R and S is 1. And that means that the GCD of r squared in S is 1. Okay. So P of r squared S is going to be P of r squared P of S. We were told we can use this factor. So P of S is, well, that's the GCD of S and 1 plus GCD of 2 and S. Let's keep them all in the same order. 1 and S, 2 and S, 3 and S. So then now the GCD of A and S can either be 1 or S. So if GCD of A and S is S, we just get a value of A equals S. Just like before, if we wanted the GCD of to be 125, our value of A had to be 125. So if we have a GCD of 1, that just means that S is not a factor of A. There's actually the only value from 1 to S that has a factor of S is S itself. So S minus 1 there's S minus 1 values of A that give us a GCD of 1. So P of S is going to be 1 times S plus S minus 1 copies of 1. And that's going to be S plus S minus 1, or 2S minus 1. And if we go back and look, well, part of what we needed is a 2S minus 1. So we're certainly on the right track. How about we look at P of R squared? Now the GCD of A and R squared, well, R is a prime. So we can either have 1R or R squared. Okay? So if our GCD is R squared, that means that R squared divides A. That gives us one such A. If we have A and R squared is R, then that means that R divides A, but R squared does not divide A. Okay? Now there's R squared, there's R many values from 1 to R squared that are multiples of R. Every rth value is a multiple of R. But there's one value from 1 to R squared that is a multiple of R squared. So we have to take that off. Now if we want GCD of A and R squared equals 1, well, that's whatever's left over. And another way of saying that is then R does not divide A, and there R squared minus R such A. So when we work that out, we get 3r squared minus 2r is the value of pr squared. PR squared s, PR squared ps, which is 3r squared minus 2r, 2s minus 1. And we can take a factor of r out of here. We get r, 3r minus 2, 2s minus 1, and that's exactly what we wanted. All right, we just double check. R, 3r minus 2, 2s minus 1. There we go. So all we had to do was sort of count how many of each type of GCD could we have. And I admit it was a little sloppy the way I did it, but I feel it's justified because we have 4 different parts here. Part A is 1, maybe 2 marks. So B part, I mean, that's the easier one of them. So B is at most 3 marks. So that's 1 mark for figuring out P of S, 1 mark for figuring out P of R squared, and I'm guessing a 3rd mark for figuring out for using this product rule up here. So the actual mechanics of figuring out P of R squared and all the nitty-gritty details of the GCD, I feel you don't really need to go into as much. So just another way you can be efficient on these questions if you start off trying to figure out, okay, where would the marks be? But we could certainly go back and do a little more work on those GCDs, explaining that a little better. All right, C part. If R and S are different primes, okay, so that immediately brings me back to part B where we had a similar setup. Prove that PR squared S can never be equal to a power of a prime number. That is, it can never be equal to t to the power of n for some prime number t and some positive integer n. Okay. They're giving us a possible outcome for p of r squared s. And we're saying it can't be equal to tn. So I think the best way to do a question like this, when they're suggesting a possible answer, is to do a proof by contradiction. We're going to assume that there are primes r and s that make this work, and we're going to show that it can't work out. It comes to a contradiction, some illogical or false statement. So let's suppose we have this setup. R and S are distinct primes, t is a prime, and n is a positive integer. Okay. Well, by B, we can expand this out. We get Tn is equal to R, 3R minus 2, 2S minus 1. Alright, so look at this equation. T divides t to the power of n, because we have at least one factor of t. And r is not 1, so t is going to have to definitely be a factor over here. R is a factor over here. R divides t. I guess actually it's probably really the only one. From there we can conclude it. So r over here, r is a factor of this, and that means r is a factor of t to the power of n. So that means r is some power of t, but r is a prime. Primes are not powers of things, they're just powers of themselves. So that means r must be equal to t. Okay. So that means 3r minus 2 is r to some power. And admittedly, this could be 0. We could have 1 over here. And 2s minus 1 is also r to some power. It could be the same power, it could be a different one. But the point is now we've gotten rid of this t. Everything is now in terms of s and r. Now, s kind of hard to get a handle on because we just have s and an r in this equation. But this first equation, there's only r's. So it's probably our best bet. So call this equation 1. And this equation 2. Let's rearrange one, and we get RA minus 3R plus 2. Now that looks very close to a quadratic, but I don't know what A could be. A might be 0, A might be 1, A might be 2. So how about we try some values? So that tells me 3R minus 2 is equal to 1. That tells me 3R is equal to 3. So R is equal to 1. Not a prime. All right. So A equals 0 isn't going to cut it. Try A equals 1. Maybe no value of A will work for any of this. And that would be where we would show our contradiction. We got to be looking out for ways to get our contradiction. So 3r minus 2 equals r. So we can rearrange that to be 2r is equal to 2. And that would mean, once again, that r is equal to 1. Will this always force r to be equal to 1? Let's try one more. I mean, I remarked already that one equation sort of looked like a quadratic when we rearranged equation 1. So maybe, just maybe, we get a quadratic. So r squared minus 3r plus 2, we can either do a quadratic formula or we can factor this ourselves. R minus 2, r minus 1, so that gives minus 3 and that gives a positive 1. So here we have a problem, r could be 1 or 2. Now that's not a prime, but 2 is a prime. Alright, so what would happen if 2 was a prime? Is there a way to discount that? Well, it would have to come from our other equation here, because equation 1 is satisfied. If r is 2, that's satisfied. We get 2 to the power of 2. And, there's nothing else from beforehand that would be contradicted, so we've got to find our contradiction. So 2s minus 1 is 2 to the power of b. And this side's always even unless b is 0, and this side is always odd. So that means b is equal to 0. So that tells us 2s minus 1 is equal to 1. So that's 2s is equal to 2, s is equal to 1, not prime. Okay. So that was if a is equal to 2. What if a is equal to 3? Well, we're going to get some cubic equation, and that's really hard to factor. So that suggests to me, because the cubic formula is not well known, that perhaps this is as far as we need to go, and there's some argument. So this work right here, it didn't rely on the fact on anything about a. It just said, okay, if r is 2, then s is not going to be a prime number, which doesn't work for us. Okay. So r must be a prime greater than or equal to 3. And I notice that this equation has 3r minus 2. So it's at this equation, this 3r minus 2 is less than r squared. Let's write that out a little better. So now we're up to a is at least 3. Okay, but r to the a is 3r minus 2. That's equation 1. But that's less than 3r, which is less than or equal to r squared, which is definitely less than r to the a. And from there, we have our contradiction, and we conclude things. So what did we do? What did we do to answer part C? We said, okay, they're trying to say we can't have an r and s that give us this equation in terms of t. And when they're giving us an actual answer, they're saying it can't be this answer, it can't be this outcome, the best thing to do is proof by contradiction. Assume that you can get that outcome and see why that'll never work out. So we said, let's assume that we can have t to the n. Well, t being prime, r being prime, that forces r and t to be equal. Then we get two equations. This first one is in r, so it's only in r, that's the one we want to look at. The second equation is in both r and s, and so at best we could get relationships between r and s, but this first one, we can just talk about r. Now we rearranged it, and we couldn't really see anything useful, so we decided, okay, let's just try different values of a. And we got a bunch of cases where r was 1, and that's not a prime, that's a contradiction. And then we got this one case where r could be 2, and we said, okay, there's nothing wrong with r being 2, so let's see if it will work in our second equation. And that forced s to not be a prime. So just by guessing that r was equal to 2, we couldn't work. It couldn't work at all. And so knowing that r can't be 2, r is still a prime, r's got to be at least 3. R is at least 3, and now at this point a is at least 3. We can get an inequality showing that r to the power of a must be less than r to the power of a, and that makes no sense. That is a contradiction. And that shows us that no value of a will satisfy equation 1. And if part of this falls apart, the whole thing falls apart, so our assumption must be wrong. And that means that we can get no distinct primes r and s to give us p of r squared s to be a power of a prime. All right. So that was C. We still have a little bit more work to do because we have D part we have to work with. Determine with justification, this is D part now, 2 positive integers m for which p of m is equal to 2, 4, 3. Now 2, 4, 3 is another number that I notice. And from part C we might be thinking powers of primes, because usually the way it goes is the earlier parts, A's and B's and C's, help you on your later parts, C's and D's. So we might already be thinking of powers of primes, and indeed 243 is a power of a prime. It's 3 to the power of 5. Okay. So there might be a way to use C to do this. Now M is, we don't know what M is. We have no idea what's going on with M. But we do know that we could prime factorize M. So let's say M is P1, e to the 1. Actually, our exponents have been, well, no, our GCDs have been A's, our exponents have been A's. Let's keep these A's in here. P2, a to the power of A2, all the way to pk, a to the k. So these are all distinct primes. And A1 through AK are all greater than or equal to 1. Okay. Well, I know that P of M then splits up into P of P to the 1, A to the 1, times P 2, A to the 2. Right? This is the rule. We are told that if A and B are relatively prime, we can split it up. And so we're just repeatedly applying that rule. All right, so P of M, and M could be any number here. We can better understand it if we just look at P of prime powers. Okay, it looks like this question's all about prime powers. So if we want P of P to the A, well, we have the sum of GCDs P to the A. That could be either 1, it could be P squared, P to the power A. Okay. We're going to have 1 less than or equal to B, less than or equal to P to the A. Now, if GCD of B, P to the A, is equal to P to the A, then we know that B is going to have to be equal to P to the A. Now, this is the exact same sort of work we did in A part, and a little bit in B part of this question. So there's one such value of b. How about the GCD of b and p to the a being p to the a minus 1? Well then, p to the a minus 1 will have to divide b, and p to the a is not allowed to divide b. Okay, b going from 1 to p to the a. So there's going to be p to the 1 minus 1 such values of b. All right, this is going to be p values from 1 to p to the a that are multiples of p to the a minus 1, and there's exactly one value that we have to exclude because it's divisible by p to the a as well. And in fact, we can generalize this. GCD of b p to the a equal, I don't know, p to the c. So p to the c will have to divide b, and p to the c plus 1 is not allowed to divide b. Well, this one, this condition here, how many multiples of p to the c are there from 1 to p to the a? Well, 1 to p to the a over p to the c. And then p to the a over p to the c plus 1. So that's how many b's give us a greatest common divisor of p to the c. So in general, p to the a, it's going to be one copy of p to the a plus p to the 1 minus 1 copies of p to the a minus 1 plus p to the 2 copies, or p to the 2 minus p to the 1 copies of p to the a minus 2, all the way up to p to the a minus 1 minus p to the a minus 2 copies of p, and p to the a minus p to the a minus 1 GCDs of 1. That's p to the a plus p to the a minus p to the a minus 1 plus p to the a minus p to the a minus 1 plus p to the a minus p to the a minus 1. So how many copies of p to the a do we have? Well, we have 1, 2, 3, all the way down to 0. So we're going to have a plus 1 copies of p to the a minus a copies of p to the a minus 1. So if we're looking at p to the power of a prime, or p of power of a prime, it's going to be a plus 1 p to the a minus a p to the a minus 1. How does this track with what we already knew? Well, we already knew p a squared was 3. That's 2 plus 1. P squared minus 2p. And we already knew that for a single prime, it's going to be 2p minus 1. These are formulas we already worked out in B. And now let's check p to the 125. Well, that's p to the 5 cubed. So So that should be 3 plus 1, 5 to the power of 3, minus 3, 5 to the power of 2. Four times 125 minus 3 times 25. Well, that's going to be 500 minus 75. Wouldn't you know it? It's 425. So our formula works. Okay? So now we can express a general P of M. Now we want P of M is equal to 243. And that's 3 to the power of 5. Okay, so we're talking about prime powers again. Now M, we already decomposed that into in terms of primes from P1 to Pk. And that tells us that each of these is going to be 3 to some power. Let's give that power a name. I guess we're up to D. And that's definitely going to be between 0 and 5. Okay. So, where can we go from here? Well, we can ask ourselves, when do we get powers of 3? So we were sort of asking this in C part. We asked, can we get a power of a prime if you have R squared and S, that sort of stuff. So now we're specifically asking, when is P of a power of a prime equal to 3? Okay. So let's suppose that 3 to the power of D, and I don't know what D is. D could be 0, D could be 1, it could be 1,000. So P to the A, well, we have a formula for that. It's A plus 1, P to the A, minus A, P to the A minus 1. And we can take out a factor of P to the A minus 1, and we're going to be left with A plus 1, P minus A. So if A minus 1 is at least 1, then we must have P is equal to 3. And that's pretty powerful. Okay? Now, if A is equal to 1, then we have 3D is equal to 2P minus 1 when we simplify the formula on the other sheet, on the other side of this page. Okay. So 2 times a prime minus 1. Now, specific to this question, we're looking for D between 0 and 5. So if D is 0, we would get P equals 1, and that's not a prime. How about 3 to the 1 is 2p minus 1? Well, that would mean p is equal to 2, and that's certainly a prime. That goes well with us. How about 3 squared? So 9 is equal to 2p minus 1. That means p is equal to 5. I'm just rearranging these in my head to sort of speed things up. $27 is equal to 2p minus 1. That means p is going to be equal to 14. That's not a prime. How about 3 to the 4? Well, that's 81. 81 is 2p minus 1. That means p is going to be equal to 41. That's a prime. That's actually sort of a surprising prime. It sort of came out of nowhere. And 3 to the power of 5. Well, that's 243. That's the one we've been talking about. 243 is equal to 2p minus 1. So that means p is going to be equal to 122, which is not a prime. Okay. So now we have, if a is equal to 1, we have all these values. All these primes that give us powers of 3. If a is equal to 0, 3d is just equal to p by itself. Actually, that doesn't make any sense. Yeah, because that would be p of 1, and we're not defining that. P of 1 is d by itself. Okay. So that's what happens when a is 1. And if a is at least 2, p is 3. So if a is at least 2, then p is 3. So 3d of, that's 3 to the a minus 1, a plus 1 times 3 minus a. And that tells me, whoops. So here we have a power of 3, here we have a power of 3, this must be a power of 3. So 3a plus 3 minus a is equal to 3d plus 1 minus a, which is a power of 3. Okay, so 2a plus 3 is a power of 3. That's fine with me. And specifically, we're going to have it's going to be between 3 to the 0 and 3 to the d plus 1, and the maximum value of d was 5, so 3 to the 6. Okay. So how about 3 to the 0 equal 2a plus 3? And that would mean that a is equal to negative 3 over 2. That's false. That can't happen. A's got to be a positive integer. Oh, 3 is equal to 2a plus 3. That also is not going to happen. A would be equal to 3 here, and that one would work. 3 cubed, 3 to the 4th, 3 to the 5th, and 3 to the 6th. This one would be a is 12. That's going to work. A is this one is the 81 minus 3 divided by 2, 39. That'll work. These numbers are getting pretty high, though. A is equal to 120, so that'll work. So maybe some power of 120 will actually give us the value that we want. And this one, A, is going to be equal to 363. Okay. So all these are fine. Alright, so now what we're basically looking for is combinations of these primes. So we could have a 2 to the 1, and that gives us a 3 to the 1. We could have 5 to the 1, that gives us a 3 squared. We could have 41, and that gives us 4 to the power of 3. Sorry, 3 to the power of 4. So p to the 3 to the 3, that's going to be 4 times 27 minus 3 times 9. So that's going to be 81. How about p times 3 to the 12? Well, it's going to be 13 times 3 to the 12. That's not going to work too high. We got our values of A that would work. Now we need to actually make sure that they're going to give us powers of 3 that we can use. So relating back to our original problem, P of M is equal to 243, which is 3 to the power of 5. And PI, AI, each of these can be either, we can get 3 to the 1 for P is equal to 2. We could get 3 squared. And that was with 5 and 1. And we get 3 to the 4, and that was with 41 and 1. And we can get 3 to the 4 in a different way, and that's with 3 and 3. So we must have a 3 to the 1 times 3 to the 4, and we can get that either with P of 2 times P 41, or P of 2 and then P of 27. So M is either 2 times 41, which is 82, or M is 2 times 3 to the 3, so 2 times 27, which is 54. And these are going to be the only 2 values of M, with P to the PM going to be our target value of 243. Alright, so we determined with justification 2 positive integers M that gave us PM equal 243, and in fact we showed that these are the only 2 possible values we can have. Alright, it was a long trip. First of all, we prime factorized M, because then we can use that rule. The rule we were given that if A and B are relatively prime, P of AB is PA times PB. Okay, so we prime factored it, and that allowed us to decompose P of m. And now we just needed to look at P of prime powers. Well, we did a little work, and we used what we knew from part A and part B to give us a general formula for P of prime powers. Using that general formula, which we know now works, we then asked, okay, well, we need powers of 3, and we need them to be sort of between 0 and 5. So what could we possibly have? Well, if we're looking at P of anything, a square, anything like that, then we're going to have P must be equal to 3. And if it's not a square, if it's just a straight prime that we're taking P of a prime, then we have a couple choices. We have P is equal to 2, gives us a power, P is equal to 5, P is equal to 41. Returning back to that case, P is equal to 3, and we're looking at a square or more. We'll have lots of different options. Most of them were too high. 3 to the 3 gave us 81, and that was our best bet. All the others were wildly too large. And then that finally gave us our options, which we put together, and we got the only two possible values. 3 to the 1 times 3 to the 4, and that gives us m could be 82 or 54. So that was a lengthy question. A lengthy question, but honestly, I think it was a good question. I liked it a lot. And yeah, I haven't really had a whole lot to say about any of the questions after the fact. It was good. Hopefully you guys tried that. Certainly D, when they asked you to determine two positive integers, you might not have needed to have been as rigorous as I was. You might just have been able to do a little guess and check. Certainly you could have used part C to rule out any squares times single primes. So that's certainly something you could do with C, and that would have eliminated a whole bunch of numbers that maybe you could have guessed and checked. Our two numbers, 82 and 54, were within the first 100 numbers, so there might have been a little guess and check work involved. Frankly, I like the way we did D. We actually figured out how to figure out P of any number, just based on its prime factorization, which I think was really cool, and would have set us up if we had parts E or F. I mean, I know we never have those on Hypatias, but it's always nice to develop a little more theory. And question 4 at least afforded us that opportunity. So, very good question. I would say the 2015 Hypatia, very good contest overall. Really liked it. And hopefully you guys did too. And I'll see you guys on the next contest, whatever that may be. If it's another Hypatia, or if maybe it's a Fryer, a Galois, or a Euclid, or something like that. I'll see you guys then. Thank you so much for watching, and I'll see you guys next time.